Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure to have Professor Baotren Li from University of Toronto to give us a talk titled "How Helpful is Network Coding?" Professor Li graduated from Tsinghua University in 1995 and then got his PhD from UIUC in the year 2000. Currently, he's associate professor and Bell University chair at ECE Department of University of Toronto. In year 2000, he also received the IEEE Communication Society Leonard G. Abraham Award in the field of communication systems. His current research interests include network coding, peer-to-peer networks, and wireless networks. Without further delay, let's hear the talk from Professor Li.
All right. Thanks, Jim. So good afternoon, or for whoever who is tuning into the video, good evening and good morning, depending on the time of the day. The topic of today's talk would be on network coding. I believe it's kind of the toughest place to give this particular talk because there has been extensive research results by Yunnan and by Phil and by Kamo Jain from the Network Research Theory group inside MSR, and also some other research results from MSR Cambridge that came out in the past several years, and especially on this topic, network coding. So if you previously had a lot of background in this area, you need to bear with me for the first couple of slides. But I believe that the talk will be still quite interesting because I have some more recent results in this particular area, especially in the practicality side of it. So let's just start with taking a look at the number of papers in network coding. From before 2003, there are about 23 papers. By the way, this is taken from Ralph Cotter's very well-known network coding page. And the other thing called the Wayback Machine, or sometimes they call it archive, Internet Archive, which takes the previous versions of the website. And I just calculated the number of papers from there. And after 2003, in the year 2004 alone, there are more than 50 papers. In 2005, there are more than almost 100 papers. And right now, we haven't concluded 2006 yet, but you can consider it to be a pretty hot and kind of debated area. So the key question here is how helpful is network coding? Especially how helpful is network coding from the practical side? So can we actually really use network coding in the practical world, in the real world? To do that, I would like to first try to progress into theory. I'd like to present some of our previous theoretical results in this particular area, and then come back to the practical side, and try to take a look at some of our practical results in the recent months or the past year on the implementation of network coding and see how practical it might be. So let's start from the very beginning, from the problem. The problem here, from the practical side, from the real-world problem, is the problem of maximizing throughput. So there has been already a lot of solutions. Most of them are very practical solutions in the systems area. The first one being CDN, Content Distribution Network. Akamai as a very good example. The second one, Digital Fountain. There has been two papers, one in 98, the other one in 2002, SIGCOMM, on the idea of using fountain codes to actually try to disseminate data in the content distribution scenario rapidly. The third example is called Splitstream, which is in 2003's SOSP, a Systems-Oriented Conference, and it tried to use multiple multicast trees to try to improve throughput from the source to multiple destinations. And finally, everybody knows about BitTorrent, the most practical protocol right now. It's peer-to-peer protocol, but the essential objective is still to maximize throughput from the source to the destinations. So the key question that we're trying to answer with the problem of maximizing throughput is, given a particular source hopefully it's one source, it could be extended to multiple sources, and a set of receivers, how do you actually maximize the throughput for each one of the sessions? So let's go to the theory. For convenience, I like to use the white background for theory. Theory is kind of on the brighter side, and practical things are on the darker sides of the world. So the white background will represent theory. When we go back to practice, you can easily see that we switch to the darker background. So the theory of network flows has been well established. It is a problem that is not too hard. There exist very efficient polynomial time solutions to it, and it is the problem of finding the maximum flow rates in the network topology with known link capacities. And if it's just a one single one-point to one-point unicast session, then it's the unicommodity flows. And otherwise, if we have multiple unicast sessions, it's multi-commodity flows. So that has been the textbook kind of scenario, a problem that has already had the very efficient centralized and distributed solutions. However, the previous problem, the setup, makes one fundamental assumption. The assumption says that this node, for each node inside that topology, can only forward the data. So this is very similar to the real world. When you have commodities, you have either liquid, oil, water, or cars on highways, traffic. You can only forward data. There are no other things you can do with a particular node inside the topology. If we consider information flows, we believe that the nodes not only can forward data, they can also replicate data. They can actually try to replicate it from upstreams to multiple downstreams. They make multiple copies inside the node, and that leads to the solution of multicast. However, beyond replication, very naturally, we can think about the idea of coding. So we can actually try to encode and decode and do whatever we wish on that particular node, since we're operating on information flows instead of commodity flows. And that leads to the recent kind of hot area of network coding. So just a summary of the comparison between information and commodity flows. Both observe link capacity constraints and the topology constraints. However, only information flow can be replicated, and only information flow can be coded. So here's a kind of a classic example of network coding. We have one source, multiple receivers. Here we have two receivers, and we would like to disseminate information flows from the source to both receivers. It's a typical multicast scenario. And we have a topology, and it's a topology constraint. And each one of the links on the topology, for simplicity, we assume that it has a capacity of 1. So the simple way of doing that is to just send a copy of the information to both sides and let them forward the data to the receiver. However, if we do that, we can observe that the middle part of the topology has been underutilized. So that leads to the intuition that we can actually try to forward different packets to different sides, let them forward to the middle node right there, and then the middle node right there can actually try to perform some coding operations and try to say if we can actually code by taking the two incoming links and perform kind of addition on a finite field. In this case, for example, exclusive OR. If we're talking about GF2, then we can actually try to forward the data to both receivers. Both receivers can recover both pieces of data, and the middle portion of this particular topology can be used. And that has been the classic example of network coding. So the key insight here of network coding has been like this. In a directed network, if we actually consider each one of the receivers just by itself, without considering any of the other receivers. For example, if we just consider the receiver on the left, then we can find two different paths going to that receiver, achieving a throughput of 2. If we consider only the receiver on the right, we can also achieve a throughput of 2 with two concurrent multiple paths. And if we try to combine both receivers, network coding has the advantage that it can help to mediate the competition or the contention around the bottleneck link, which is this one, the overlapping link between the two sides. And just achieve the same throughput as if none of the other receivers existed. So in this case, network coding can help to try to utilize link capacities without any competition at all from the other receivers. And that has been shown in landmark papers in this particular area in directed networks. So one of the things that one can consider is the idea of undirected networks. What the definition of undirected networks is that links are not directional. They're bidirectional. Not only they're bidirectional, they can also allow the flow rates to be arbitrarily split among two directions. So it is a bit more general model than directed networks. And in some cases, it is also a harder model than directed networks, in the sense that it is a model that is at least different. We give one example here. The example that holds in directed settings no longer hold in the undirected network. Here's the example of a very simple triangle topology where the M0 is the source, M1, M2, they are both receivers. And we would like to send at the maximum flow rate from the source to both receivers. And what we're trying to do here, if we have a directed network, we say that we can ignore the other receivers, and if we can achieve a throughput of whatever to one of the receivers, it can be achieved for the entire network. Now, if we take the same theorem applied to the undirected network, then to M1 we have two paths and we can achieve a throughput of 2. To M2 we also have two paths. We hopefully can also achieve a throughput of 2. But that's not the case for undirected networks. For undirected networks, since this particular link, you can only split the unit capacity of 1 to two different directions. You cannot basically say, I would like to achieve a capacity of 1 for each direction. We can only achieve a capacity of 1 for the total of the two directions. In this case, you cannot achieve a throughput of 2 for each one of the receivers. So undirected network is slightly different as compared to directed networks. The other category that we can probably consider is the category of fractional versus integral routing. Now, the fractional routing basically says that if we have a link capacity of 1, we can divide that into arbitrarily fine granularities. We can actually say we'd like to send a throughput of 0.4 on this particular subflow, 0.6 on the other subflow, while integral routing basically says all of the flow rates should have integer values. If you have a capacity of 10, then you cannot basically split that to 0.5 and 9.5. You have to use integers. So we later will show that these are also two different cases. So let's try to consider the previous example again. But this time, let's try to consider the case where we do not use coding. Now, if we do not use coding, what is the best we can actually do? What is the maximum flow rate we can actually achieve? Now, previously we have shown a way to achieve a flow rate of 1, but without using any of the the nodes and the 5 links in the middle. However, that may not be the best that we can actually do with this particular topology. For example, what we can do on the example on the left side would be we would like to split this entire topology into 3 different trees. Each tree had a capacity of 0.5. And then while each one of the link capacities are not violated, each one of the link capacities, if you add them up, it's still 1. However, on each one of the receivers, what you can receive is data on all 3 trees, which means that you can actually achieve a throughput of 1.5 instead of just 1, because you are actually using some of the capacities in the middle instead of just completely wasting them. So the question at this point is that can we actually try to utilize even more out of this particular topology? Can we actually pack even more trees? If we allow fractional routing, which means that we can arbitrarily split the actual link capacity into fine granularities, then we can actually try to have 9 trees in this particular case. We can actually try to say if we label the tree as A, B, C, D, E, F, that tree will have a capacity of 0.25, while if we label the tree as 1, 2, 3, then that tree will have the capacity of 0.125. And we can say that each one of the link capacities are still not violated. However, on the receiver, we receive the information on all 9 trees, which add up to a throughput of 1.875, which is very, very close to 2 already. So in this particular case, we are basically trying to say, can we actually try to even do better than this, 1.875, without using coding? Obviously, using coding, we have 2. So that is a traditional problem of packing. If we are talking about the broadcast scenario, it's spanning tree packing. If we're talking about the multicast scenario, it's Steiner tree packing. The idea here is that we like to iterate through all different possible combinations of splitting and packing more trees into this particular topology so that the link capacities are not violated and the total tree weights are maximized. So in this particular case, we can see that it is possible to pack that many trees inside this topology, and we can achieve more than just having one tree. But it looks like, for example, even in this particular scenario, no matter how we pack more trees into this topology, it still cannot achieve the throughput that is higher than coding. So coding is still the upper bound. So that leads to a natural question called the coding advantage. The coding advantage is the ratio of the best throughput that you can actually achieve of using network coding versus the best that you can achieve with routing only. So, and that is called the packing number, the actual result of solving the packing problem. So the key question here is that what is the coding advantage? What is actually the additional throughput that coding can actually provide? So in some of the previous work that we have been doing back in 2004, we actually have cases where in fractional and half-integer routing, where half-integers are allowed, we show that for unicast sessions, single unicast sessions, broadcast sessions, just one broadcast session, the coding advantage is 1, which means that there's no coding advantage. And for a single multicast session, the coding advantage is upper bounded by 2. Now that is actually quite interesting because this is in the case of undirected networks. While in directed networks, there has been previous papers before this paper, some of the papers published, the earliest ones in 2003, saying that the coding advantage is not bounded, which means that you can actually have contrived examples of the topology in directed networks where using network coding can actually offer unbounded advantage as compared to not using network coding. So again, in undirected networks, we also have a conjecture which has not been solved yet, but has been previously verified by Kamal Jain here at Microsoft and Lehman at MIT, that in special cases it is true. The conjecture is the coding advantage, even if we consider multiple unicast sessions allow inter-session coding, is also 1, which means that network coding also does not offer any advantage if we are taking into account multiple unicast sessions. Yes?
To go back how the advantage is defined, is it a ratio?
The ratio of the best throughput that you can achieve with network coding, which is 2 in that particular example, and the best that you can achieve without network coding, which is the Steiner tree packing number. So that is the ratio here. So the other very interesting concept that is related to the connectivity of this topology is called the strength. While in spanning trees, it's related to spanning trees, which is broadcast sessions, it's called the network strength. And in the multicast case, it's called the Steiner strength. Now, the strength is defined using a concept called the partition of the network. The partition of the network is like this. You would like to partition the network so that each partition at least contains a source or a receiver. So the source and receiver should be at least one of them should be in each component inside the partition. And the Steiner strength is defined as the minimum ratio of the total intercomponent link capacity. In this case, the total intercomponent link capacity is 6. 1, 2, 3, 4, 5, 6. and over the total number of components minus 1. In this case, we have 4 components minus 1 is 3. 6 over 3 is 2, which means that the strength of this is 2. This obviously is very convenient because this is already the minimum. We have already found a partition that offers the minimum ratio. So in this case, the strength of this particular example is 2. Now, since we have previously shown that in this example, network coding can also achieve a throughput, a maximum throughput of 2, the key question here is whether or not it's possible to actually try to say the 2 is exactly the same. Now, it turns out that the strength is not that easy to compute. So even if they're the same, it's not that important, not that interesting. So we would like to define throughput as the maximum throughput, which is the maximum information flow rate that we can achieve with coding, with fractional routing, and in undirected networks. Now we have an example, we have a conclusion saying that the throughput is actually in between the packing number and the strength. So the strength, even though in the previous example is 2 and the throughput is also 2, in very rare cases, strength could be larger than the throughput. Yes?
What's the implication of the strength? I didn't...
It's like a definition that kind of characterizes, it's like edge connectivity. It's a definition that characterizes how connected the topology is.
So it's a concept about connectivity. No?
It is, yes. It's one of the concepts that characterizes.
It's not directly related.
Right, exactly. The throughput is not directly related to connectivity, but a better connectivity implies a better throughput. And the same thing applies to the packing number. So if you can pack more, then it implies that a better throughput. So these two are both kind of different ways of characterizing the connectivity and the throughput inside the network. And they're both kind of combinatorial concepts inside the graph.
There's at least one, right? There's always at least one.
Right. So what we would what we'd like to figure out is that the packing number and the strength, they're both NP-hard problems, which means that they're both not very useful in terms of calculating that throughput. So the benefit of network coding in the theoretical sense with a white background is that throughput can actually be computed in polynomial time. This maximum throughput with network coding inside the case of fractional routing and inside undirected networks can be computed in polynomial time. So this has been shown using a linear programming formulation and by solving an LP problem. Yes?
So you will give example practically what's the underlying model for undirected network, right?
The underlying, well, yes, I will. I will talk about that, exactly.
I know people is using integral routing, is it?
Right now, it's very hard to say. You can call packet-based routing integral routing because it's not fractional in the sense that fractional meaning that it has to be fractional flows. The flows has to be dividable in fractional granularities. While if you're using a packet switched network, it may not be fractional. However, that is not a very interesting discussion because it's an approximate.
Because I think whether or not it's fractional or integral depends on the timescale you're looking at the packet.
That's right. Exactly.
So if you enlarge the timescale big enough, then the come and leave dynamics of the packet just goes away, and then you can approximate the through model.
That's right. That's right. Okay. But I will come back to the idea of integral routing a bit later.
Okay.
So the key question on the theory side is how does network coding help? I believe Yunnan has studied this problem for a long, long time. His thesis is on this particular problem. And the key question here, as summarized by not only our papers, but Yunnan's thesis, and a lot of other PhD theses and other papers, is very clear at this particular point. The point of network coding is that we would like to leverage its power to resolve the competition for link capacities, which means that now we can take the maximum of flows competing for capacity, for link capacity, instead of the sum of them. So that makes it much more tractable. So network coding enables much more efficient computation of the maximum throughput. That includes, from previous papers, both the problem of finding a strategy to flow, kind of how to divide a particular link to different flows, and finding the strategy to assign codes for that. So both of them are polynomial time. In polynomial time, there exist polynomial time algorithms for them. So that kind of, on the theoretical side, is the benefit of network coding. So let's recap a little bit on the fractional routing case in the undirected network. The problem is to compute this multicast rate in this particular case using network coding. Without coding, it is a fractional standard tree packing. It's an NP-complete problem. However, with coding, we can actually make it an LP problem, which is polynomial time. The other very interesting result is the complexity of the problem of computing multicast, the maximum multicast throughput problem in integral routing case. So inside the integral routing case, we still use undirected networks, but now we change from fractional into integral routing. Without coding, it's very interesting. The integral standard tree packing problem, while NP hard obviously, is actually harder than the fractional case. In this case, only polynomial time approximation that is known is a 26 approximation. And that is only recently discovered with approximation ratio of 26. While with coding, the problem obviously is still NP hard, but the polynomial time approximation algorithm can be a 2 approximation, which means that it can have approximation ratio of 2. And that has been shown in the in CIS's 2004 paper that we have previously had. So in the previous case, in the fractional routing case, network coding enables changing from NP hard problem to a polynomial time problem. And in the integral routing, even though both are still NP hard, with integral standard tree packing without using coding, we can only have 26 approximation. With coding, we can actually have a 2 approximation algorithm. So here are the good and bad news. The good news is that the throughput problem is more tractable with network coding. The bad news is that we have been running quite a lot of simulations trying to take a look at the coding advantage in different kind of topologies, and we have been randomly chosen topology, randomly generating topologies. No matter what, in the case where we have single multicast session, the coding advantage is always 1, which means that it really is not that interesting to talk about throughput improvements. It is more interesting to say that even though the throughput achievable by packing is good enough, it's very high, but it is not tractable problem, while the throughput problem using coding is a tractable problem. So now we progressed from the white background to the black background. So the idea here is that we'd like to ask the question. So given all the theoretical research, not only our own papers, but also other people's papers in the past several years, hundreds of papers every year, how practical is network coding in the real world? So we're interested in this problem because we would like to probably file some patents for this, if that's patentable technology, to actually try to use it in some sense. So the first intuition is that it is probably practical, in the sense that even though we do not probably have the capability of modifying core Cisco routers, we can actually try to use coding, network coding, in N hosts at the edge of the internet, which leads us to the discussion of peer-to-peer applications. So is it possible to actually try to perform coding in peer-to-peer applications? Sure, it is possible. We can do that in the N hosts. At the application layer. However, how practical it is. Does it offer a benefit at all? So let's revisit the undirected network previously set up. We previously say that the undirected network is theoretically a little bit interesting, but we never claim that it is more practical. In fact, the undirected network is probably even less practical than the directed case. Because even though the internet is a bidirectional link, it offers bidirectional links, it is not a strictly undirected network in the sense that you cannot arbitrarily split, the flow rates between two different directions, the opposite directions. So we believe that the internet is more of a balanced bidirectional network, which means that it's not a directed network. While it is also not a strictly undirected network, it's more of a balanced bidirectional network. And the coding advantage can be easily shown in this particular case if we have a balance of alpha, a balanced ratio of alpha, which means that the flow rate, maximum flow rate on this direction is no more than alpha times the flow rates of the other direction, then the coding advantage is still upper bounded by 2 times alpha plus 1. So in this particular case, we can still have a coding advantage, upper bound of coding advantage, but this discussion is moot because it really does not offer any insights on the answer of the previous question: how practical is network coding? So, does network coding help? Well, there exist some intuitive roadblocks. One roadblock is that the flows, we're going to have to wait for the incoming flows, the other incoming flows, so that they can be coded together, and then generate the outgoing flow to the downstream nodes inside the topology. And that probably will lead to additional delays or something like that, kind of like an intuition here that I call the penalty of synchrony. Now, the other question is link capacity, while in previous examples in theoretical cases are assumed to be known, very well known. We know the capacity constraint, but in the internet, in the real world, they're not known. It's impossible to know these capacities. And the key question we'd like to explore here is how realistic is coding in current generation systems, in current generation computers? How realistic it is to perform coding at all? So to actually get rid of the question of code assignment and other things, back in 2003 there has been multiple papers almost concurrently discussing the idea of randomized network coding, including Yunnan's paper called Practical Network Coding, which I will come back to later. So the key insight here is that all the deterministic code assignment algorithms, they're okay with their polynomial time, but they're not practical. We don't want to use them. They involve too much message passing overhead. So what we're going to do is that we're not going to do any code assignment algorithm at all. We're going to randomly generate all the coding coefficients on all the nodes inside the entire network to form the basis and leading to practical network coding. So the idea here is that each node will transmit on each outgoing link a linear combination of incoming packets from incoming links, and these random coefficients are randomly generated from some finite field. So let's take a look at previous results on practical network coding and see what do they say. The very first paper on practical network coding is a paper called Practical Network Coding, obviously. Authored by Phil and Yunnan back in 2003. I just want to quote one of the sentences inside the paper. The result is a practical system for network coding that is robust to all kinds of different problems like random packet loss, delays, any changes in network topology, capacity, and it can achieve close to the theoretically optimal performance. Very upbeat, very optimistic. Let's take a look at another one. Infocom 2005, Microsoft research again, but this time in Cambridge. The Avalanche project, they try to say the performance benefits provided by network coding in terms of throughput in the content distribution scenario can be more than 2 to 3 times faster as compared to not using coding at all. Very optimistic, probably even more so than the previous paper. Well, there's some people, especially led by the inventor of BitTorrent, Brad Cohen, who is currently, in Silicon Valley, busy doing his startup. He had this blog in livejournal.com, and the blog says, he doesn't like the paper of Infocom 2005. I doubt that he read it, but he said that badly missing from this paper is back-of-the-envelope calculations about on-the-wire overhead, CPU usage, memory usage, and disk access time. Basically saying that this paper does not take system parameters into perspective. Now, the Microsoft Research Cambridge, what they did is that they really did an implementation. So just to, I don't know for what reason, but it's probably to counter the previous argument, they say that let's implement it in the real world C# implementation, deploy randomized network coding used in content distribution in 100 peers, a few of them, about 4 or 5 of them DSL peers, around the world, mostly around Microsoft Research sites around the world. And they published a paper reporting results. And one of the sentences inside the paper is called, network coding incurs very little overhead, both in terms of CPU and input-output, and it results in smooth and fast downloads. So, but there's one key question about this paper. The paper talks about using network coding in content distribution, but it never compares using network coding with the case of not using network coding. So it doesn't want to compare, or doesn't have the capability to compare with something like BitTorrent. So it is still a question. While most recently in the keynote at the second workshop on network coding, Raymond Young, who is one of the inventors of network coding, basically says in his paper, can network coding help in peer-to-peer networks? A very grand title. Obviously, this is the question that everybody would like to know the answer to. In simple star peer-to-peer network models, there is no coding advantage. Fine, we know that there's no coding advantage, but we're comparing, when we talk about coding advantage, with Steiner tree packing, which is not tractable. Can we actually try to use it for, in peer-to-peer networks to, improve throughput, as compared to not using packing, to existing ways like BitTorrent? So, to answer the question, how does network coding help in practical scenarios, the key question is, can we actually just give it a try? Why don't we just give it a try and see how a real-world implementation works, instead of just try to read papers? So, and believe what other people will say or will not say. So, there are some of the problems with this particular approach. Well, the first problem is that the experimental results are not very repeatable. If you have 100 peers around the world, you don't have the full control of these peers. Hopefully, these are borrowed accounts from your peers, your colleagues in your lab. And these peers, they're highly dynamic. They come and go, and it's very hard to repeat the experimental result. The other thing, it's very hard to involve a large number of peers. So with 100 peers, probably it's the largest number you can manage. More than that, it's very hard to involve that number, and it's very hard to involve DSL cable connections, peers that are with home broadband connections. However, in the real world, those are, the most of the peers are with cable and DSL connections. The other question here is that it's very hard to collect the results. Once we have those experiments, very hard to collect those results. If you set up a logging server, if you have ever tried, and establish connections back to the logging server, it's equivalent to a denial of service attack, distributed denial of service attack, as you have more and more peers inside the network. So it's very hard to actually know what is the result. And finally, in general, it's very hard to implement this thing from scratch. If you take a look at a popular Java BitTorrent client, it has 262,000 lines of Java code. And actually, to implement something that is trying to say, let's compare with BitTorrent, at least you're going to have the same kind of caliber, the same fine-tuned implementation. And with this kind of scale of implementation, it's very hard to achieve. Probably only Microsoft Research can do this. Nobody else in the world would be able to do this. So we would like to give it a try. Even though we being just myself, I would like to just try to run some cases in a testbed. So I'm going to have to admit I have no control. I have no friends in this world. Nobody's going to give me their computers for me to have full control. So we like to emulate computers inside a cluster of high-performance servers. So the other benefit of doing this is that it's a fully controlled environment. The entire cluster belongs to me. I would like to run these experiments right now with this random number generator and this seed. I can. And it will be fully repeatable and controllable. So that gives the insight of developing such a testbed. So I actually try to do so. So I would like to design a testbed so that I can have hundreds of emulated, if not thousands, of emulated peers in a single server, so that if I have 100 servers, that could have 100,000 peers. completely emulated inside the cluster. Obviously, I would like to implement the randomized network coding. I'd like to process incoming messages and produce the outgoing ones, just to try it out. And all the operations will be on finite field GF256. So the one key problem with this approach is that your cluster is not the internet. Your cluster had tons of bandwidth across different nodes inside the cluster. So what we're going to do is that we're going to have to arbitrarily emulate the actual bandwidth constraints, either on the link or on the node. On the node being, for example, a DSL connection, uploading is 1 megabits per second, downloading is 5. That's something that happens in the real world. We'd like to emulate that. So in this particular testbed, we supported the emulation of total uplink, total downlink, and total bandwidth limits. We'd like to emulate them all. And we'd like to be able to start, kind of bootstrap this entire emulation using arbitrary initial topologies. So here's an illustration of what we have implemented. So we have implemented, obviously, the coding, and part of the engine that tries to process incoming blocks and incoming messages from multiple upstream nodes and send them out to multiple downstream nodes. And each one of these links, we can put bandwidth limits on the link, or we can say we'd like to put a bandwidth limit on the entire node, uploading, downloading, subject to this particular limit. And within the actual coding engine, we like to have a buffer. The buffer had accumulated blocks so far. There's nothing new with this buffer. It has been proposed back in 2003 in the practical network coding paper. And the decoding begins after a particular criteria is met. For example, sufficient number of blocks received, or some particular point. We're going to get back to this point a bit later. So that's what we have implemented. Some challenges. The first thing is that, if you're going to use, try to evaluate network coding, you're going to first have to make sure you're going to have the best implementation of network coding. You're not going to use Java, or whatever that uses a virtual machine that basically implements network coding. We would like to implement it from scratch using a lower level, high level programming language such as C++. Right now we did use C++ for this with the best compile time optimization. So that is our attempt to achieve the best possible performance using network coding, performing network coding. And the other challenge is we have all the emulation of this bandwidth caps, this per link, per node bandwidth limits. All this emulation code should not take CPU, because if they do take CPU, then all the CPU is taken away from the coding engine. We'd like to devote most of the CPU cycles to the coding engine just to give it a try and see how it works. So we have tried to spend a lot of time trying to optimize the code so that the CPU load is minimized and everything is fine-tuned so that we use the minimum number of threads, and there's no overhead in emulating the bandwidth limits. The lower the bandwidth limits are, the smaller the load is on CPU. So that's just a very high level overview of what we have done on the coding side. It's easy to say, it's extremely hard to do. Takes tons of time for us to actually get that done. But it's great that we already have that. So let's give it a try and see what we can do with this particular engine and to evaluate network coding. So the first thing we'd like to evaluate is so-called the coding performance. So basically, this answers the question on exactly how realistic is it to perform coding in current generation CPUs, in current generation computers. So to do that, we'd like to simplify that to a very simple one-to-one session. Just me and Jin talking. Each on the fast CPU we can ever find back in 2005. Well, it's purchased in 2005 because the funding expires by the end of that year. But it has to be dedicated. It has to be the fastest CPU we can actually get by that time, and we got it. So everything's optimized, and let's look at the results. So the results is not very stellar, so it's not very optimistic. So let's first take a look at the encoding bandwidth in terms of how many bytes can you encode per second. Well, obviously it depends. It depends not only the number of blocks that you have, and also depends on the block size. How many bytes do you have in each block? It turns out the block size itself is not that important in the sense that if you change the block size, it doesn't change the the encoding bandwidth too much. But there exists the optimal value somewhere around 2 kbytes to 4 kbytes is probably the optimal value, but it really doesn't matter too much. It turns out the parameter the utmost important is the number of blocks that you would like to code. And if we increase the number of blocks from, let's say, 10 all the way to 1,500, you can see it dramatically affects the bandwidth of network coding, produced by network coding, all the way from, on the y-axis, this is actually bytes per second, so 10 megabytes per second, down to 22 kbytes per second if you go from 10 blocks to 1,500 blocks, which means that really it's not feasible to increase the number of blocks. Most likely, you would like to stay with probably 100 blocks, 50 blocks, something like that, a very small number. The other very surprising result is that I just switched to the other slide. It's not a same slide. It's a different slide. The difference is that now we are measuring the decoding bandwidth. Now, it turns out the decoding bandwidth is exactly the same as the coding bandwidth, as the encoding bandwidth, even though decoding had matrix inversion, full matrix inversion, and encoding does not have that. Encoding simply performs GF operations for each one of the bytes and send them out. Now, here decoding would like to inverse the entire matrix. It does not matter. The decoding bandwidth is almost exactly the same as the encoding bandwidth and follows almost exactly the same trend, which argues that for both decoding and encoding, the block size itself is not the key point here. The key point is the number of blocks for each segment or each generation. Now, here's kind of a more detailed view of how much time did we spend on different components of this coding. Now, if we take a look at smaller bytes, kind of smaller number of blocks or kind of smaller block sizes, then we can see that it takes more time for the matrix inversion and so on. Because this is just a ratio. This is a ratio as compared to the actual time of performing GF operations for every byte. So obviously, if we have a smaller block size, we spend less time on that. But for the more typical sizes, for example, 4K per block, 100 blocks, we can actually see that most of the time is actually spent on the actual GF operations, the encoding and decoding. The matrix inversion and generating the encoding matrix does not take that much time, as compared to the time of encoding and decoding.
So from your previous two slides, it seems that my guess is system is I/O bounded. It's not CPU bounded.
It is CPU bounded because everything is performed.
But you have to read it
inside memory. There's no I/O here.
Yeah, but memory also consumes I/O, and then you have how many nodes do you simulate per each CPU?
It is how many nodes? Well, we only simulate one, so we dedicate the entire CPU to that one, to that one net coding engine, and see what's the maximum block size can it sustain.
Okay, it's just encoding and decoding throughput. I can see basically when the block goes basically long, most probably it's you're missing CPU cache, so that's why basically the throughput decreases. I mean,
because matrix inversion is a very heavy task for
The reason is that the matrix is very small. It's only, for example, 1,000 by 1,000. Inverting a matrix like that is not a big deal. We will come back to this point, by the way. We will come back to the coding performance a bit later. However, with some of the more recent results that we have been doing, that is even more fine-tuned. But this one gives you a general idea of, for example, encoding is the same time as decoding. Yes?
Yeah, I think I missed something. In the previous slide, what was the x-axis?
The previous slide, the axis is the number of blocks that you encode. That's right. Right, exactly. Inside the generation. Or we can call it a group in Cambridge paper.
So what does the group mean here?
Oh, it's the number of bytes you can produce per second. Or,
Then you're generating at different coding rate, right? So with smaller generation size, the coding rate is high. And obviously, you have to spend more time doing that.
well, this is about bytes per second, right? This is not second. The unit is bytes per second, right?
Basically, for smaller say if you do 1 megabyte per block, and the generation size is 25. After one encoding or decoding, you generate 25 megabytes.
So the analogy here is that if you have, for example, a link with 1 megabytes per second link, you can keep up with that link if we have full CPU power devoted to coding, because the decoding bandwidth is about the same. So, but any faster links you cannot keep up. You're going to have to do it with more time.
Just checking. I mean, I assume in your basically Galois field multiplication, you use a lookup table approach.
We will come back to that point. We have optimized that. We have optimized that. We'll come back. Yes, right now we use a lookup table in this particular graph, which is actually not too good, because a lookup table takes memory. Takes memory access. And memory access is well, it is faster, but but memory access is still not fast enough. We still want to access memory. Later on, we are trying to take it so that we minimize the access to memory. So here's another slide, basically saying that the final slide on coding the coding performance is that if we send the file, just to send a file of 13 megabytes. Using the coding engine from one end to the other end, there's nothing in between. There's a gigabit Ethernet network. Just send it out, and depending on the number of blocks, it takes a tremendous amount of time. Let's say if you use 200 blocks, it takes almost 100 seconds, which is 2 minutes. So it takes a very long time just to send that file. This gives you another way of thinking that really it takes quite some time to actually try to encode on one side, decode on the other side, and in the meantime, the transmission does not take any time, and the matrix inversion does not take any time. Only time is taken by encoding and decoding, and this is C++ and fully optimized at compile time. And we will come back to the coding performance. So let's take that coding engine and try to take a look at more realistic topologies. So with more realistic topologies, we would like to try 50 servers, each one of them dual CPU. Each of the 100 nodes has its dedicated CPU. So we put 2 nodes per dual CPU server, which means that 1 node per CPU. By node, I mean an emulated node inside an emulation framework. Just to make sure that CPU is not a problem. We're not competing for CPU in any sense. And in the other consideration that we have is that since the large number of blocks is a problem, then we use a small number of blocks. We use 50 blocks, 4 kilobytes per block, just the standard number. 50 blocks is small enough, it's not a big deal. Even in previous coding performance, with 50 blocks, you can actually have a very high coding in terms of throughput. And in terms of comparison, let's just compare with the worst possible protocol. The absolutely worst possible protocol that one can actually use to disseminate data from source to the multiple receivers. And this is called naive broadcast, just by myself. And the idea here is that each peer, when it receives something, it just forwards to all its downstream neighbors that it knows of. Whenever it receives any duplicate, it just simply discard the duplicate. Bandwidth is consumed and wasted. Usually it leads to, experimental results say that, depending obviously on the topology, it leads to at least 300% bandwidth waste. So it wastes a lot of bandwidth using this particular broadcast protocol. And any real-world protocol, including any buffer map exchanges, anything that have any content reconciliation, such as BitTorrent, is much better than this. At least 300% better than something like this. Let's just compare with coding with using network coding with naive broadcast, and let's try to vary the actual network settings. So different cases, we have 2/mixed, saying that each node will have 2 downstream neighbors, and it's a mixed scenario in terms of per node bandwidth constraints. By mixed, I mean 30% are Ethernet users and 70% are DSL users. And for pure DSL, we mean that 100% of the nodes are DSL users with a particular upload and download bandwidth constraint that is very similar to the real-world DSL. And pure Ethernet basically say everybody is Ethernet. But no matter what we're going to do is that we're going to compare with coding and naive broadcast, and we can see the green bars the lighter green bars is the downloading time for coding, and the darker green is the downloading time for the naive broadcast. And it turns out that in no cases we can actually find coding can beat naive broadcast. So every time we try it out, naive broadcast actually beats coding. No matter what's the network scenario, what we're actually trying to evaluate here. However, if we look at the actual orange and the pink bars, we can see that really coding does not waste any bandwidth. We try to send 100 blocks, and we really send 100 blocks. However, naive broadcast wasted tremendous amount of bandwidth. Probably 300% more blocks are being passed throughout the entire network. But still, naive broadcast can actually try to beat coding. And the other cases where we try to vary the number of downstream peers in a particular mixed topology, no matter what we do, no matter what kind of parameter we set, there's no way that coding can beat naive broadcast.
So why the number percentage has
120%?
And basically, it's the percentage of blocks that naive broadcast has been received and discarded, obviously. So it wastes tremendous amount of bandwidth, but still completes download faster. And we're not using a lot of blocks. We're only using 50 blocks for coding, which is very fast.
So when you say it downloads faster, you don't consider any bandwidth limitation, right?
Right. So we consider all the constraints on the DSL or the Ethernet. We emulate them, 30% Ethernet or 70% DSL or full DSL or full Ethernet. We change the scenario, emulate all of them, but cannot find a case where coding can beat naive broadcast. So now we'd like to tune for a little bit better performance on the coding side. So first thing we can do here is we can decide how many new incoming blocks do we wait for before we generate one outgoing coded block. So previously we have been waiting for all of them to come in before we generate. We can actually wait for less. So let's wait for less. And we call it aggressiveness. And we try to say, let's be more aggressive to produce outgoing blocks. And the other thing we call it density, which is how many blocks do we actually sample, randomly sample, for the outgoing block to be generated, to be coded, inside all the buffer blocks that we have inside the buffer. We don't want to sample all of them. Let's sample a few of them. Should be good enough. So that's what we call density. Now, it turns out that we change, first of all, the density to be from 100 blocks and 100% to fewer. It turns out that really we kind of the average downloading time for the coding case, which is the yellow line, is actually improving as we actually change the density to be lower and lower. The downloading time is improving. However, the last data point here is naive broadcast. As you can see, no matter how it improves, it still cannot beat naive broadcast. And there's a bit of a problem in terms of here. When your density is too low, you have the linear dependence problem, which means that some of the nodes cannot fully decode. They have linear dependence because your density is way too low.
Just a question.
Yes.
I assume it equals 1, right? It should be exactly equal to naive broadcast. But it seems...
You mean density equals to 1?
Yeah.
So here, this point is not density equals to 1. That's just a naive broadcast.
In that case, does that mean the coding for if you use density 2 and 4 performs better than naive?
No, this basically it does not perform better because this is not measurable because all of them cannot decode at all. They simply cannot decode. The green one shows the percentage nodes who can decode after receiving 100 blocks. So you're going to have to consider density more than 6 and see that's the best that we can do with coding. And
The density for example, each access point, you just take that density and the random sample. You're not saying my density follows some kind of distribution.
no, we just take a particular density. Let's say 6% and just send it. Just code 6% of the buffer blocks, send them out. Which is actually pretty low because we only have 50 blocks anyway, for the coding, and it's only a few blocks. So, but still, it cannot beat that. And let's change aggressiveness as well. Let's try to make it, more aggressive from waiting for everybody to waiting for less and less and less. But it turns out that around 66% for the aggressiveness, we observe a much larger number of nodes who actually observe linear dependence, which means that a large number of nodes cannot decode. So the green line shows the percentage of peers who can decode after receiving exactly 100 blocks. A large number of them cannot decode. However, above 66, yes, changing the aggressiveness did improve, the downloading time in the coding case. But again, the last data point is naive broadcast. As you can see, it approaches naive broadcast but cannot beat it. So, the downloading time really cannot be better than the worst possible protocol that we can ever imagine. We can write in 100 lines of code for naive broadcast, and coding cannot beat that. So, the other question is, what happened to those nodes that failed to receive 100 linearly independent blocks? Don't we just say that, in previous papers say that, it's a high probability everybody receives linearly independent blocks. So the key question here is that, we have observed, this is actually some measurement data from the real observation inside the real emulation. This is not a contrived example. We have observed that when you actually try to be too aggressive, which means that you try to start coding too soon, you actually, try to send to your neighbors, data that is linearly dependent to whatever they receive from their other neighbors, which means that you are kind of a small clique inside, and you're trying to pass, vectors of coefficients inside that little clique, and that those vectors, they're linearly dependent. So it turns out that we cannot be way too aggressive. Aggressiveness has to be, there's a lower bound we can actually make it to be, and the same applies to density. So the other thing we have tried is that we try to put in linear dependence checks, which means that once something's linearly dependent, we just throw it away, get another one. If it's linearly dependent, throw it away. Well, it turns out it doesn't add too much time in terms of computation because it's just a very small matrix. It's a 50 by 50 matrix. So it's not a big deal. So it's fine, and we can actually have a very nice curve here in terms of the downloading time. However, it's still not better than naive broadcast. The same applies to when we change aggressiveness. Still, when it reaches 66, which is around the best that it can do, around the same as naive broadcast, not beating it. So the key question here is that naive broadcast is really not a good protocol. If you have something like BitTorrent, I'm pretty sure that can beat naive broadcast by 200%, probably. So in this particular case, the key question left on the table is, what can network coding do? Exactly, does it help in peer-to-peer networks? So we have some ongoing work on changing the coding engine. So previously, the key question here is that the key observation inside that experiment is that most of the time is done on coding. And we don't want, that much time done on coding. We wanted, the minimum amount of time done on coding. And hopefully, we'd like to make it the world best implementation of this, random linear coding. So we have some ongoing work on using the SSE instruction set on Intel chips to accelerate the implementation of it. And before we do that, we had an even more fine-tuned baseline implementation of network coding, which achieves about a 20% to 50% improvement on top of the previous version that we have just shown in the previous slides. So that's already a good improvement. 50% is pretty good, depending on the scenario of number of blocks versus block size. However, we would also like to add SSE2 acceleration, depending on the Intel chip, and we'd like to make it cross-platform compatible. So we can compile it on Linux, on Mac OS 10, on Windows XP. Mac OS 10 these days Apple is using Intel chips, so that's not a problem. We are working on the previous generation PowerPC chips, acceleration using so-called LTVEC, instruction set, also very similar to SSE acceleration. It's kind of a vector instruction set. So the result is that encoding time is still about the same as decoding. Really, that fact never changed. However, we are pretty confident at this particular point that the results probably would be the best that anyone can achieve with commodity CPUs at this point. Because you don't have any additional tools. You have SSE, you have LTVAC, depending on the chip. The only other way is to use non-commodity hardware instead of commodity CPUs. Using commodity CPU, this is probably the best. So what are the results that we have? So we can actually achieve, depending on the hardware, depending on the number of blocks and the block size, about 300%, all the way to about 900 to 1,000% better than the base implementation. So the base implementation is the no SSE2, the red bars, and the SSE2 implementation, they're actually the blue bars. So as you can see here, depending on the actual hardware, if it's a Mac Core Duo or if it's a Windows XP Intel, the previous generation Pentium 4 2.0, Linux Opteron AMD chip, Linux Intel Pentium 4 Xeon 3.6, depending on the actual hardware, it's slightly different in terms of the speed up using SSE, but it is a dramatic speed up. It's about 5%, 500% more advanced as compared to the the no SSE version. And the no SSE version here is already an improved version as compared to the previous generation implementation that we had. And the first four scenarios are using 256 bytes per block and 256 blocks and 1,024 bytes per block. If we change that to 256 blocks and 4K bytes per block, we observe slightly more, which means that 4K is actually better than 1K, slightly better performance. However, if we change 256 to 1,024 blocks, it again dramatically degrades. No matter if we use SSE or not use SSE, as compared to the previous case, it dramatically degrades. In this particular case, the y-axis megabytes per second. So if we use 124 blocks, as you can see here, we have 560 kbytes per second, which is pretty good, but it's much better than 90 kbytes without using SSE, but not stellar. So what exactly is the conclusion after this ongoing work that we're currently doing? By the way, this has not been published. We just concluded this particular study. Is first of all, the coding on a single peer, on commodity CPUs, probably it is reasonable if we have fewer than 1,024 blocks used. Because if you really want to sustain current generation streaming rates, you probably would like to use fewer than that, 124 blocks, 1,024 blocks. And obviously, you're going to have to use Intel or AMD chips that supports SSE2 acceleration. However, the coding on a server is a different problem. It is a big problem because a server had a much higher bandwidth to saturate. To saturate a typical server bandwidth, very typical, these days you can buy them almost for free, 100 megabits per second connection on the server. You're going to have to use fewer than 32 blocks, even though if we enable SSE2 acceleration. So this basically, it's too small of a number that, if we use only 32 blocks, probably we even increase the probability of having linear dependence across different vectors. And again, if we're talking about coding on layer 2 and layer 3 switches, which even had more link capacities, it's virtually impossible at this particular point. Coding in wireless nodes, the only thing I can say is not sure about it because really, you don't want to use 100% CPU on that wireless node. And that wireless node CPU is at least 2 orders of magnitude slower than your typical PC. And certainly, when you use 100% CPU there, the energy consumption will be huge. Probably not very sure, even though right now we have tons of paper trying to talk about using network coding in wireless and in sensor networks. If you use GF256 coding instead of only exclusive force, I'm not very sure about wireless networks. And finally, network coding, which means that you don't want to consider only one server, one peer, one wireless node. You want to consider the entire network. Everybody's going to have to code. Could still be challenging when used in practice. That's the ongoing result, and I welcome any questions I'm very happy you can still this late. You can try to stay this late into the kind of Friday afternoon right after the company meeting, and feel free to have any questions.
Do you consider that